So, welcome to the second part of the introduction to fastAI. So, this is unit 8, I think, part 2. And now we look at NLP. I hope this video will be a lot shorter than the last one because we already discussed all the basic principles and ideas of all but the basic here. We discussed the basic principles and ideas of fastAI. And now we'll apply it to natural language processing. This time I'll just show you the IPython notebook on GitHub for this lesson with natural language processing, because here we use some training which takes, especially the language model training, fine-tuning, which we'll see in a second. It takes a long time, so I thought it's easiest to just show it in the notebook, because running it, some steps take a few hours, which is a bit long. Okay, so we do use fastAI here on the IMDb dataset. So IMDb, that's this IMDb dataset. So IMDb, you probably know, is the Internet Movie Database. So it's just a website which has movies and descriptions and all kinds of information about the movies, and also some reviews of those movies where people tell about if they like or don't like a movie. And we look specifically at those movie reviews, and we want to classify if a movie review is positive or negative about the movie. Maybe this sounds simple, but it's not simple at all, because here in this data set, so let's have a look at the description. Here we have a data set of 100,000 reviews, but we need, or we specifically are interested in the 25,000 which are labeled as positive or negative, and we use this for training. And those reviews, they are in the form of such textual descriptions about the movie. And we have this textual description, and as you can see here, so let's maybe start from the beginning to make it easier. So why it's difficult, what I wanted to explain now, I get back to that into a second. So what do we do? So we have this data set. Then in the first cell here we again do just this please plot the graphs inside the GitHub page or whatever. So just some configuration. Then we load now from fastAI text everything which is in there. And okay, now we're ready to get the dataset, which we do in this command. So in this command we download the dataset, same command we used for the image dataset. Then we look at the files which we got with the path.ls, and see that there are a couple of files. What's interesting for us now is the texts file, because in there we have the texts and the ratings. They also include some pre-trained models. All the other stuff in there, it's basically models, but we want to train it ourselves. So we have this, we look at this texts CSV file, and we open it. It's a CSV file, so one easy way to look at a CSV file is just using pandas to make it into a data frame. So we open this file, then we show the head, the first couple of rows of this data frame which we just loaded. And we see that in this file, we have rows, and the rows, they represent the reviews. Every review in the column, the first column, column 0, however you start to count. So the first column is negative or positive, so the label of the data. Then second column is the text, so which is there, but we don't show everything because it's a long text of maybe hundreds of words potentially. And then we have a third column which tells us if this should be in the validation set or in the training set. So for this we don't need to, or yeah, it's recommended to use their split into training and validation set, and we can just see it in the third column where the example goes. Okay, if we look at the text of one row, so row number 1, then we can see, okay, the review, it looks something like this. And okay, so what is the problem now? We have 25,000 positive, negative text like this, and nothing else. So if we would only use this text and those 25,000 labels, well, it's quite a sparse signal. And it would work. You could even use like SVM classifier or any kind of classifier on this, or neural classifier. But probably it will not be that great, because it will usually, those approaches, they just use a bag of words model, so they don't really learn the meaning of sentences of text. So if we use this basic approach, we would probably learn, okay, there is a word like cruelty and cruel in here, but there's also love in here, so there are different words, and then we might basically in a very simple way count which is more positive or negative words. So the classifier would do something like this if it doesn't understand the text. Understand not like a human, but have like a better understanding than just looking at the words that appear like in a bag of words approach. Okay, what I wanted to say, in the basic approach, probably we will, because we don't have so much training data, 25,000, it's not little, but it's not millions. It will probably not be so great. So what can we do? And this is then in the next step, I'm jumping a little bit ahead, to have some more knowledge of language encoded. So this is like the main part of making fastAI really great with this task. It again uses pre-trained models to improve the classification, which we want to do later. Okay, but let's go step by step. So now we are at the point where we basically just downloaded the files, and we have this text CSV file with our reviews. Then we want to create a data bunch. Again, in this time it's really simple. We have to already explain this. We now make two models. First, we train a language model, and then we train the classification model. For the language model, we do for both things, we do the same steps. Load the data, so creating the data bunch, training it, and then maybe saving and evaluating it. So for the language model, we start with the step 1 with loading the data. And we do this here in this line. We create the data bunch with the path and the texts CSV, so it's very simple. Okay. Okay, I just looked ahead a bit. These next couple of cells are just to show what is happening when you create a data bunch from text. So we load the data, this text file, and create a data bunch. This takes a little bit of time, so this is why Jeremy Howard, also saves then the result of this without training, just the data bunch itself. Why does it take a little bit of time? Because for text, we also want to have it, and it's automatically done, to do some additional steps like tokenization and numericalization. Tokenization, we already know what it is. So the text itself is just a long string, so it then gets split into tokens, which we can then use later in our models. fastAI does some things which I need to explain a little bit. So you see there are the tokens, but there are some strange tokens in there. Some tokens starting with XX. And those are special tokens created by fastAI to give some additional information to the model. So I think XS BOS is probably beginning of sentence BOS. So it just makes an extra token to let the model know, okay, here there's a new sentence. And then there are many tokens like XXMHA, and I think these are the tokens probably that are not in the vocabulary. So fastAI, to make things more efficient, uses a fixed size vocabulary for which you can define the size of the vocabulary. For example, 50,000 words you want to have in your vocabulary. So the 50,000 most frequent words will be in your vocabulary, and all words which are not in this list will then just be replaced by this token. Although I think this token which we're looking for here is the XX unknown. So these are the words which are not in the vocabulary. XSMAIJ. So we would need to look into the documentation what this tag exactly does. What's the difference to the unknown token? For our purposes, it's not necessary to understand this in detail. So you can look it up in the book, in the documentation, if you're interested. Okay, so first step is tokenization. So then we have the list of tokens. It also does things like, for example, isn't is split into basically two tokens, is, not, which helps then with the model, just to have this fixed set of tokens. All punctuation is it's kept, so we don't have any removal of stop words or punctuation in there. Because often in language models you do want to keep all tokens, because you want to emulate how humans use language. And we humans, we don't skip stop words when we speak. So you want to keep everything as it is, but you do a lower casing as you see in there. You just split everything into single tokens, like even punctuation is its own token, and so on. Here is some explanation of some things which would be done. The content, for example, it's also cleaned from any HTML symbols. It should only be the text. If this is created from some HTML source, you want to obviously get rid of any HTML code from the text. Okay, when you have it tokenized, we want to now numericalize our data, which just means we want to replace the strings with numbers to make it more efficient. And so we have already our vocabulary now created. It's in data.vocab. And then we can have a look, maybe that's the best thing to do, to see that if we print it to the user, so now we have a training set, the training data set. We print here one training sample. And if we look at the data that is used internally, then instead of the words which we have here internally, it's just a list of those numbers, which are just the mappings between the number and the word in the vocabulary. But this is a more efficient format to store the information than using the words itself. Okay, I think this is enough for because you probably will never need to change any of these things. Tokenization, maybe tokenization in some cases you want to do adopt it. This numericalization, it's just for the internal speed up of the training process, basically. Okay, so this was just to show how this works internally. Now we want to look, so this is basically here, we start from here. So after downloading the file, which we already have now we want to create our data bunch. This time we do it in a little bit different way. We use the data block API. And in this API, it works something like this. So you have some text list, which is just a list of text documents. And you want to say we create this list of text documents from a CSV file, because our input file is a CSV file. And we want to say where the CSV file is. It's in this path, it has this name, and we are now, for the language model, which we look at now, we are interested in the text column. We are not interested in the other columns. We'll see in a second why. So we want a text column, And then we want to split it into training and testing according to column 2. And column 2 was this column, as you maybe remember, is valid. So we want to use this column to split into training and validation. We don't need to do it like with another. We could also do it randomly, but we use this column because we already have it. Okay, we're here. Okay, and here we still use the labels, or we still assign the labels from column 0. Although now for the language model, okay, this is actually also this, it's just to show how it works. We will see it later. So now here with language model, actually the training process starts. So to create this data bunch, we could use for the classification, we could do it like this. We say where's the text, we split it according to this into training and validation, and we say on which column is the label, and we make it into a data bunch. So now we have all the information which is needed to train the model. So the first step with NLP tasks is because in the classifier we want to use a language model as input, and the language model has information on how language is used. So it helps you with the classification because it can encode your text with this language model which you create. You can encode the text with the language model and then use this in the classification process. Using this language model is much better than just having this simple bag of words approaches, because language models, they understand the use of language, and they can give you a better understanding of language, what it means in your classifier. In the course, in the online course, I think he uses the example why language model, or to show how language models are understanding text. If you have a good language model, then you would have, if you have two examples. One example I think was I like to eat hot X. And the language model, as we learned, a language model predicts the next word after a sequence of words. So if you have as input, I want to eat a hot, and then you want to predict the next word, then a good language model would probably maybe say hot dog, because it's about eating, so hot dog or hot, I don't know, hot soup, something like this. But if you have another sentence, today it is very hot, and you make the prediction from there, then you would probably want something like hot day or hot weather. So it very much depends on the context, which word you want to predict. And if you have like a bigram or trigram language model, then you just don't have the context to predict the next word. And he also gave the example, if you have a really good language model, then it's like almost like like understanding the knowledge of humans in a philosophical way. For example, if you have a language model like in 1994, the president of the United States named X did something. And if you then want to predict the next word, then you need to have a lot of world knowledge to predict the next word correctly to the name of the American president in 1994. So this shows this usually a language model cannot do yet. Although if you train it maybe on a large corpus, it might work sometimes. But yeah, you see that the language model, it has needs a lot of language understanding and even world knowledge, common world knowledge, to have to be a good language model. So we want to train, we want to use a language model in our classification system. And again, we want to use transfer learning. So included in fastAI, there are language models. The most typical one, it's a language model trained on Wikipedia or on a subset of Wikipedia, but with over 1 billion tokens. So you have a lot of input to learn this model. It's pre-trained with an LSTM. We learned what LSTMs are in PyTorch lectures. So you have a pre-trained LSTM language model of Wikipedia. But this, in the video he said, I think it trained 2 or 3 days on a very good hardware. So with, I don't know if multiple GPUs, at least on one fast GPU. So we don't want to train this model ourselves. We could, but it doesn't make any sense. So we use this model, but then with what we want to do is we want to fine-tune the model to our domain. So this is the crucial step. If we work in the movies, for example, if we look at movie reviews, they probably use a different kind of they have a different use of language than like Wikipedia has. Or if you have tweets on Twitter, they use a slightly different language. Or especially if you have medical text, then you have a very different vocabulary, but you still have, you use English language, but you use it a little bit differently. So you want to use transfer learning then to fine-tune the language model, which you have the general language model, to your domain to have like a domain-specific language model. And this is what is done here in the next couple of steps, which we can have a look at. So, okay, basically here you don't need all the code which was above, was just to give some examples on how to use things. I think the notebook basically it starts here. So if you run it from here, it should be fine. So we set the batch size, which is just a parameter. Then, okay, we even start with downloading, so you can definitely use it from here. I don't know why he put all this information up there, but okay, it's fine. So we download the data, we'll download our IMDb dataset. Then we have a look. Let's see, what is it different? Okay, it seems like in the dataset there are different ways. There on the one hand there's this test txt file with the text, but it looks also like it's also in separate directories where all the data is positioned. So if we look inside the downloaded dataset, we have some training directory, and in there's a positive and a negative directory in this training directory. And okay, you can read this, but what we want to do now here is create a data bunch for our language model training. So we go to this path where our data lies. So we create a text list from this path, and we want to only include the folders which either have the training data, the testing data, or unsupervised. It just means it has no labels, it's just the text of the reviews. But for the language model we don't need the labels, we just need the text. So we can use all these texts from these directories for our language model. Then we randomly split it here, so we don't use the information from this text file. We randomly split into 10% validation and 90% training data. Okay, then we label so we just tell the data bunch that this is like we want to train a language model here with this label for language model, and we make it into a data bunch given our batch size. And then we can save this object if we want, because this also already does the tokenization and everything, so it takes a little bit of time to create this this object. Okay, we could also load it again, so if we continue next time, and then we can look at what the batches look like. So here we just have, it's just the text, and yeah, it's just the text in there. So for the language model we only need the text to create, to fine-tune our language model. We just need the movie text to make a language model for movie text. Okay, so we have documents in there. Okay, that's fine, and now we can already create the learner to learn the language model, which we tell here. And we have our data object, which was the data which we have up there, which we created for the movie reviews. And then we have this AWD LSTM. This is the language model trained on Wikipedia, which we want to fine-tune. So we have our data, we have the original language model, the big one, which we want to fine-tune, and we have some for some, you can just, it's about dropouts for the training. Yeah, it's, Not sure if we discussed dropout yet, but this is something more like for the machine learning course, not for our course. It's not so relevant. Just keep the defaults. Okay, so we have defined the learner. Then we can look which learning rate should we use to learn our model. We call this LR-find method, and then as a second step you can put it into one cell. You just want to plot what the LR-find has found, and now you can see your curve, and here it's quite simple to understand which learning rate might make sense. So the lowest point is here at 1 e minus to the minus 1, so 1, so 0.1, and this. So we said that we can, from here, from the lowest point, we can go maybe a factor 10 back, or we look at where it's the steepest slope. And so in this 1e2, 1e minus 2 is here in this region, it's going down the most. So I think, yeah, he used this as the learning rate in this model. Okay, then we call this fit one cycle, like we did. So this is all the same, like we did with vision, how you train it. These steps are all the same, finding the learning rate and then running this fit method. And then we see we have, after one epoch, we have an accuracy of 0.3 almost, which means that when you have like a couple of words, you predict the next word, that with 30% accuracy you pick the predicted word is the correct word, which is actually quite nice, because in language, you, even as a human, you don't know. If you say, I want to eat hot something, it could be soup, it could be dog, it could be grecha, or whatever you want to eat. So there is no clear thing which to the prediction is not so easy. So I think you understand what I want to say. So in 30% having the word which was in the text, this is already really nice, which we have here in this language model. Then we can save after training, we can load it again if we continue on the next day, so this is just optional steps. And then again, so if we train it like this, then we only trained the last layer or layers which were added. But we can again do this unfreeze to train the whole model, so which they do here. So they unfreeze the whole model, so all the layers are trained, and then train for 10 cycles here. And with a little bit lower learning rate, because it's already trained, so we probably don't want to jump so far. So he took a learning rate like divided by 10 of the original learning rate and trained some further. And as you can see here, this trained for 3 hours and 8 minutes. So this is why I did not want to do it like interactively this time, because yeah, that's no fun to wait such a long time. So and this also you don't need to only need to do when you have in your real-world application. For our toy project, we will use a much smaller data where it trains quickly. But if you should really use this in your job or somewhere, then you only need to train your domain-specific language model once, probably. Because when you work, for example, in the legal domain and you work with law text, you train one time a good language model for law text. Then you can use it maybe for part of speech tagging and for classification and for different things or whatever in having the language model to if you have it on a phone for some law app and you want to type text to predict the next word or so you can use the same language model. You don't need to train it all the time. Okay, then he saved this final language model again, and as you can see, the accuracy is now a little bit better, so it's at 34%, which is yeah, probably you won't get much higher than that, because just as said, text, it's just too variable you can never get 100%. That wouldn't make any sense. And we can see, maybe at looking at the training loss stuff, in the beginning training loss is higher than validation loss, so it's still underfitted. And then in the end you can see the training loss is lower, so this means okay, the metric looks fine, so this probably means okay, here it's enough training, definitely, because it's not improving anymore, and validation loss is not getting lower anymore here. and it's below the training loss, so it's enough training. Okay, and as a final thing, now we have the movie language model. We could use this language model to just generate text, like artificially generate text, which we do in this cell here. So we predict for a range, let's go here, n sentences is 2. So we make 2 sentences, and we want to make 40 words for the sentence, so we predict 40 words in 2 sentences. And we give as input, we give just this thing, I like this movie because, and then we let the model predict. This is not optimized to do good text generation. This should just show you that the language model somehow understands how sentences in the movie domain look like. So what did it generate? I like this movie because, okay, this was the input, of next word predicted the, so you do it, so the predictions step by step. You always get the input and predict the next word. Because of the cool scenery, so this looks really like a movie, description of a movie, and the high level of British hunting. So it doesn't make sense, but it's not intended to make sense, it's very hard to have a language model that really makes that. You need a really good understanding of the world to make good sentences, but it should be like the language of a movie review. He only thing this movie, okay, this is not correct grammar, so it's not perfect. Movie has going for it is the horrible acting and no script. Okay, so this, you can obviously see this again is some fragment which probably occurs in reviews. I like this movie because it was one of the few movies that made me laugh so hard. Okay, that's really good, at least so far. So hard I didn't like it. It was a hilarious film and it was very entertaining. So yeah, this is like the typical speech in some kind of review, which is here predicted. So we see the language model seems to be very good. So we can use it in a classifier. Finally, we save the encoder, which the encoder is basically the part that encodes a sentence for predicting the next word. So it encodes the text into some internal representation. And this is what we want to use for the classifier. We get an input text, we encode it into an internal representation in the neural network, and then classify based on this representation. So we save this part of the model that does the encoding here, and use it then in the classifier. So in the classifier, let's do this a little bit more quickly. I didn't want to make the movies always so long. In classifier now we have the same thing. We download the data. I mean, we already have it, so this would be like if you start the notebook again. Then first step, you create the data bunch. So again, we have a text list. We say our data is in some folder with a path. We give it the vocabulary of the language model. That's important to that in the language model we have the same, mapping from numbers to words like in our classifier. So else it wouldn't work, obviously. So we just need to give, we need to use as vocabulary in the classifier the same vocabulary which was used in the language model. So we just give it to the classifier here. Then we split it into training and testing by a folder, because we have one folder, train and test, so we can just use this folder structure to create a training and validation or test datasets. And then we label it, this time by the folder names, because as you remember the folder names, there was a folder negative and one positive, and we can just use this for labeling our data for the classifier. And then finally we create data, so we make it into a data bunch, so we have this data bunch. And we can save it again if we want. We can load it after saving. So then we can show this data bunch with some batches of this data bunch. So we have the text. As you can see, it's tokenized, and some tokens are replaced by some artificial tokens. And we have now the target. So because now we want to do the classification, so now we need the labels which we want to predict. So we have the labels, positive and negative, and the text. So this is enough for our classification problem. Okay, now we can already start with the classification learning, which is here. So again, we create a text classifier learner. We give it the classifier, the data bunch which we created with the text and the labels. We give it the language model. I think this is used for the architecture of the language model. So we give it the original language model, the pre-trained. We say something about the dropout, and then and as a next step we load our encoder. So here probably it only uses the architecture to know which architecture of language model, which neural network architecture the language model uses, and here we load the weights which we trained previously for the movie language model. Okay, so we have the language model inside our learner. And then we can start. We can do a learning rate.find and plot. Okay, here the plotting is not shown, so you would have some kind of graph. We find the learning rate 2 multiplied by e to the minus 2, so it's very similar to the learning rate we used here. So probably we had a similar graph, maybe a little bit shifted, very little to the left, or not. So this learning rate is almost, so it's like you choose it from your feeling, so it's not, and it just needs a little bit of experience to get some reasonable learning rate. We were here. Okay, so we fit for one cycle again. So this is again the frozen model where we only now fit the last layer or layers which we added. We get already to an accuracy of 92%. So only with 3 minutes of training the classifier itself, so the language model we already have, we get already to 92% of accuracy. Although this classification problem is a bit easier because we only have 2 classes to predict, so it's a binary classification. It's not like in the case with images where we had 37, I think, animals to choose from. But still, so it's very nice that we already have 92% after just a little bit of training. Okay, then here what we want to do in NLP classification. This is one thing explained in by the course also, is we want to gradually unfreeze the network. So we first trained only the last part, the very last part. Then we want to train one layer additionally, one more previous layer, and then we want to train more and more of the network, starting from the end. To slowly go with the updates through the network to using this, to improve the network like this. I hope this was understandable. So what you do, you train the frozen network with only the last layer trained. Then you unfreeze to one more layer from the back and train it again. And train it some more, let's say that's to improve it. And here, okay, for learning rate here again they used this slice, which means that the last layer will be trained a little bit more with a higher learning rate, and the previous layers will be trained with a little bit less learning rate. So this is basically what's done here in this slice thing. Okay, and then we have an accuracy after 4 minutes of 93.7%. So we are improving, very cool. Then we unfreeze some more, one -3, so we add one more layer, and again we can train. Okay, and usually in between you would call the learning rate find and plot to see after each step what is now a suitable learning rate. So I think this is maybe not shown in this notebook for some reason, because the learning rate also changes from here. It's higher, then it gets lower. So I think he will probably, what was done when this was created, to in between they probably had this learning rate calls to see what is a suitable learning rate. Okay, training some more, and now we have a little bit more accuracy. And then finally we unfreeze the whole network and again train it some more. Again, the learning rate should here be evaluated what is suitable. Then you train it again, and then we end up at 94.3 accuracy. And okay, this is basically it for the training. And then in this case, we didn't do much evaluation, which we could do with this interpretation class to see what are the examples with the top losses, for example. So which movie reviews were incorrectly predicted, and maybe look at them. Maybe there's something, maybe it's sarcasm in there. So they sound like they're positive, but actually they're negative about the movie, stuff like that, which maybe the model didn't, which is very difficult to understand for a computer. Maybe it was something like that. Okay, and then finally we can use this for prediction. That's like any model, so we could give it an input review. Here it's a very short one. I really loved that movie, it was awesome, so it's obviously positive. And it gives you category positive as prediction, so yeah, worked very nicely. And it gives you also the probabilities, or not the logits, yeah, the output of the model. So it is probably the probabilities. Yeah, probably. So it's with 99.9%, it thought it's positive, and with the rest of the probability mass, it thought it's negative. So the classifier was very sure that this is a positive review. Okay, that's it for this lecture. This time there will be no homework for your course. Next time we will look at NLP classification on some more research case, with not using LSTM for creating the language model, but using some probably BERT, which is a very new and very new 2019 or 18 was so it's quite new, and it's transformer based model, so not LSTM, and those are very popular now in NLP, used for in most state-of-the-art stuff. They use now these transformer models. So it's just another way of creating basically the representation of the sentences, which we then use for the classification. And we look at the different use case of legal text next time, to have some other examples and see what are the difficulties and problems there. Okay, that's it. Thank you, and see you next week.